So, so the topic of the talk is safety constraints or safety guarantees under uncertainties, right? So we had like some talks who addressed the problem. You had like some of this notion in your talk, and also others. I tried to look from this direction more in the context of adaptive control. We had like the pleasure to have Andrea had a talk before. So you have like some context of MRAC and adaptive control, which is great. So, I think, yeah, from there on, hopefully my talk will be easier to digest. What is important is that the results I show you are really joint work. As Sang said, I had the pleasure to visit MIT to work with Anu on control barrier functions, right? And that's where I was introduced to the topic, and also worked together with Peter since then. So all the things you see are really like joint work. The motivation, I think, is clear, right? So I don't need to talk a lot about it. So we have like a lot of safety problems in general, which we have to address. And there are plenty of applications which have certain constraints that could be different constraints. Now you see a very nice way of looking to swarming, right? Coming straight from South Korea, right? Where they have like UAV swarms really like operating in densely dense operations together, and you need to ensure that they don't collide with each other. There are examples of urban air mobility where you have like different air taxis or small drones who are operating in cities where you need to make sure that they don't collide with each other. Hypersonic scramjet, for example, where you need to make sure that the angle of attack range is somehow in a certain range, because otherwise the intake is not in the best conditions, right? And with that you lose performance. Classical problem is coming here from Boeing, where they have like a fighter jet with load constraints. You need to make sure that the load constraints are not violated, otherwise your system could fail. And also here on the lower side, you're seeing a small, very interesting snake-like robot, which is trying to get through like gaps. And also that could be like somehow addressed through control barrier functions, right? Or a state constraints, and with that as control barrier functions. And these are like the motivations. I will, of course, not address all of those problems in general, but it's just like nice to have this in the back of your head. The talk today will have like basically three points or topics. So today I will first revisit and recap on the foundations of control barrier functions in a way that helps me to present the work we have done in combining control barrier function with adaptive control, right? And from there on, very simple outlook and conclusions. So the concepts of control barrier function, right? So we had the pleasure to have a very nice talk from Victor right in the morning, right? So he laid the foundations. And just to recap on this, right, we could imagine we have a nonlinear continuous system, right? Control affine. And for this system, we could search for a continuously differentiable function h, right? Which is defined such that within a closed set, which we call S, like our safe set, the function is positive in a way that it's greater or equal when it's within the set. Means on the boundary, it's the function is 0, and then within the safe set in the interior, it's greater to 0, right? And when we found this function, or when we have this function, we can actually use it to enforce safety, right? And also this is nothing new. We had it today already. So we have this constraint, this inequality constraint, which is basically saying we have this full term here is h dot, right? And we just need to make sure that h dot is lower bounded to this term here, right? And this term could be anything actually. So it has to be a class K function. And what we normally do is like searching for an exponential function, but that we're having an exponential lower bound, right? What that means is that you choose this function alpha such that you have a parameter, call it gamma, call it whatever, it's a scalar, times the value, the barrier function itself. And with that, you get like an exponential lower bound, and you need to make sure that your system operates above this lower bound, right? And with that, you're safe. And in general, the idea is like to have a generalization of Nagam's theorem, right? So you need to make sure that the system stays safe in a certain way. And as Victor already talked about, this is the most popular way to do this, right? And how does this help us? We already had this also already today. So the idea of using control barrier function is that you can decouple safety from performance, right? So you can now have a performance-oriented controller in the most simple way. So it could be anything. So I just like wrote down this. And normally you plug in this controller into your dynamics, could be the plant, and you're designing the controller with respect to performance, robustness, etc. But in that sense, or in this way, the controller is not able to provide safety, right? So what will happen is that, for example, you could have a controller for a drone, and if the drone is not aware of surroundings or has no module that informs the drone of this, you will basically have performance guarantees, but no safety guarantees. So you will bump into a pillar that is right in front of you, right? And using control barrier functions, we could actually keep the controller as it is and plug in an additional module, right? Our CBF QP safety filter right here. And we're trying to filter the input coming from the controller in this way, where we have the cost function, which is often chosen to be like in the Euclidean norm, right? So we have then in the quadratic program, we have a complex problem, and we have here our safety constraint, right? And when we do this, we can actually ensure safety, right? So the safety filter tries to balance between safety and performance. And as long as the safety is not conflicted with the performance, you're trying to do whatever you would like to do. However, if a constraint is active, right, this QP will give you a solution that is trying to be minimal invasive, but still safe, right? And this is like what you can see here on the trajectory. So the simple example, right? When you use this exponential control barrier functions, you have basically one design parameter, which is gamma in this case, right? You have this scalar gamma, which you have to choose. And also, as the others talked about, this design choice has implications. So theoretically, you could choose gamma as you like, right? For a system without input constraints, for example. However, the world is not like that. And normally, the choice of gamma is also part of your, let's say, synthesis, right? So you have to choose it properly, and it has implications on your actuators. And it also has implications on the way you render your system safe, right? So if you're choosing a conservative gamma, normally for like a relative degree system, the lower gamma is, the more conservative you are. Is that you're actually, in the case, for example, here with collision avoidance, the lower you choose gamma, the more far away you initiate your avoidance maneuver, right? And the higher you get, the closer you get to the obstacle. And if you would choose gamma, let's say infinitely high, you will actually impose Nagam's theorem, right? So you would just impose h dot greater than or equal to 0 at the boundary. So what you basically would do is, if you want to go there, you would go on a straight line. And once you reach the surface of the obstacle, you would scratch around to get to this point. So it has, like, if you're very confident about your system and your actuators, you can choose gamma as high as you like. But if you're less confident about it and you have problems, you have to choose it in a wisely manner, and it will be interesting afterwards. Okay, so keep this in mind. Now I talked about mostly of systems with relative degree of 1, right? What we also have to consider, we have systems of higher orders. And what that means is if you're deriving your safety constraints and you have the V derivatives, you have this term here, right? If this is 0, it means you have no control authority in the sense of safety, right? So you're not able to use your controllers to render the system safe. So and this means hopefully just the problem of having a higher relative degree, and there you use higher order control barrier functions to have a backstepping like approach to get your safety constraint, right? So you start with the safety function you think is correct, or not correct, but it's like the one that is for the operation is helpful, and then you're having like a recursive way of deriving a higher order control barrier function until you get the point where this part is not 0 anymore, right? Like backstepping. If your controller variable or your control input is showing up in the equations, you're good to go, right? And then the last function that you're using will become the input constraints you have to the inequality constraint you have to put in your credit program, right? It's a very simple approach, and it works quite okay. Of course, theoretically, you have no guarantee that the one you're deriving is actually the real control barrier function of the system, right? But in a more heuristic way, or let's say in a practical way, you often get to the point that it's like it can practically ensure safety, right? In a certain area, and you have to be careful about it. What I mean is that if you look, for example, into a system which is, I think, familiar for us, we have a longitudinal dynamics of a missile system, right? And here we're using NDI control the system, right? So we're having an angle of attack command and a cascaded NDI controller that translates the angle of attack command into pitch rate command, and from there on you convert it into the surface deflection, right? And this is how you would do it. I think I would just assume most of us are familiar how this works, right? So I won't discuss it too much. However, if you do it in this way, you could get to the point where your alpha reference maybe tries to do something which is not valid or shouldn't be done by your missile system, right? For example, you have load constraints, and the alpha command you choose is actually with respect to the operating point and then pressure you have is leading to load overload of the system, right? You could end up in a case where you have structural limits that are violated, right? Normally you would define such problem in the flight envelope. This is what you're seeing here, right? And then like within a defined minimal speed and maximum speed, you should be in a certain range of loads, and normally those loads are a function of the stall limit as well as the structural limit, and you convert this back to angle of attack constraints, and you can actually use this to derive a control barrier function. So now I'll just focus on the upper limit on this, because the lower limit is basically the same thing, just on the other side. The easiest way would be to define such a safety function. It would be the straightforward control barrier function to apply. And from there on, again, the cookbook example, you're having this function as your first choice. You're having some assumptions on the constraints you're looking into. For example, you have alpha max. You just assume that point-wise, this alpha max is constant. And with that, the time derivative on alpha on this constraint is 0. And if you do this, you can derive the first the first derivative of this, and you still see there is no delta showing up, right? You just have like alpha dot, but alpha dot is also not a function of your control surface deflection. When you have this as your exponential, like your alpha function, right? And then you have one step again, an additional step, and then you get to the point that you have alpha dot dot, right? And alpha dot dot is basically a function of your delta again, and therefore you have now the point reached where you have your system. Normally, basically, it's like when you have like a system, second order system, you will normally get to this point, right? So you need two steps for this, which is basically, I think, the majority of aerospace systems. And when you got that, like in this case, you need to do some ways of approximating alpha dot dot and rephrase it to delta. But this shouldn't be that important for us right now. But the more important thing is you get to the point where you can use this constraint, right? And again, alpha dot dot is a function of delta. And if you know that, you can plug this in your QP, which you apply to the system. And in this case, we are on an operating point where the store limit is the relevant one, right? So we have a store limit for the missile system of 15 degrees, but we give in a reference of 20 degrees, right? And we should try to ensure that the missile system stays always under this red line. And you see it always does. And actually, the different lines you're seeing here are different values of gamma, right? And there you see what I meant before with the choice of gamma is the design choice you have to make with respect to how you want to make the system safe, right? If you choose gamma in a certain way, you have like a very steep increase, right? And with that, higher demands of the actuators, right? I think you can see that. And also actually implications on the rates, right? And if you have actuators with rate constraints, you should be very careful about it. If you're not that confident that your actuators are getting into saturations, you rather choose a different gamma, right? Again, it's like a design choice and you have to be aware of it. This is like one example, and there are further examples actually in place. So for example, this is from some colleague at DLR, which uses control barrier functions for collision avoidance of autonomous helicopters, right? And there you see basically the same thing, right? Higher order control barrier functions applied now to position constraints. We had it with others before. This works quite well. And actually also here, so these are robust control barrier functions. So it's like something coming from the University of Michigan, right? From Dimitri Panagu and I think Joseph Bredin, where they basically found a way to design control barrier functions with input constraints for higher order systems. In this case here, we applied it for cooperative missile systems, right? So you have missile systems which are individually distributed tasks within each other. But the problem is once they receive the task, the trajectory optimization is individually, right? And they have just like limited knowledge of what the others are doing. If this is not respected or not considered, for example, with safety filters, you end up in a case where the systems, as you see here, are colliding with each other, right? Because they have like two targets which they try to intercept, which are also very close. And using safety filters, you can actually make sure that this is not happening, right? So they can have like partial information of the others. And with this, you are still able to render the system safe. So here we implemented the safety filter using the robust control barrier function. And you see the ones that collided before are now flying next to each other until one is intercepting the other. And with that, it's outside of the simulation, right? And then after that, the other one is making the approach. So therefore, you can ensure safety with that, right? So again, it's with this simple approaches, you can have like actually some real world applications without like thinking too much about it. But of course, once you get to the point of real integration, the problem gets much more difficult and you need to be aware of certain things. For the ones that are not just starting with control barrier function and never used it, there's like in my GitHub page, I have like some very simple, small examples, which are maybe interested for the ones who are trying to play around with this. So if you're interested, have a look, yeah, play around, right? So yeah, with this said, this is like just the basic control barrier function stuff, right? I think the message of today is like control barrier functions are a powerful tool, and you can have a lot of applications where you can use it. Theoretically, you could argue that you can separate performance-oriented controllers or the performance aspect from the safety aspect and using safety filters to just impose safety. But there are still like things you have to consider, especially with respect to actuation limits and model uncertainties, which will be the next step. Okay. Any questions so far about this? Good. So it was just a recap. Yeah.
So in the missiles, you are using the predictive CBFs.
No, well, point wise. Yeah, they were solved point wise, so no prediction at all. You have like some predictions, but yeah, these predictions are okay. Let's say like, these are predictions in terms of zero effort miss. Yeah, this is like very different. This is like basically you're saying, okay, I know at one point the closing speed between me and my agent, right? And then you're kind of like extrapolating this to like if let's say an intercept point or like a collision point, right?
Okay. And then once they select like the targets, then it's just drive to that point.
Yeah. So you have a performance-oriented, in this case, actually simple proportional navigation guidance, right? So they're trying to intercept directly. And at the same time, you have the safety filter that computes the relative velocities between each others. And based on that, tries to render the system safe. Right? Those are roughly the concept. Yeah, when you have safety filters, there are problems. Actually, there are a lot of problems, and I think this is actually what keeps all the people awake who are working on this. You see, like when you plug in the safety filter just after your controller, it's just part of truth that you can just like plug it in and think it's fine. If you have, for example, integral states within your controller, you could end up like in cases where you have wind up, right? So you need to be aware of that and probably need like some methods to address this. And also, this is also important, keep this in mind. If you have a controller, a robust controller with robustness guarantees, right? If you have a safety filter, just applied right after your controller input, you can destroy your robustness guarantees, right? When the constraints here are active, the closed loop holes or the dynamics that you have designed within your controller without having a safety filter in the loop are not in there anymore, right? So with that, your guarantees are gone, and you keep this in mind. So with that said, there are further problems. You have input limits, you have uncertainties in the model itself, the one you're using the safety filter, and of course, always possibly unknown external disturbances, right? The one I would like to address in the further talk is model uncertainties, right? And model uncertainties could occur from different ways, So maybe you have like a bad aerodynamic model, so the CFD model you received is not that good, but you could also have a problem such as the F-16 where half of your wing is gone, right? Or the Airbus here where your engine is basically also destroyed, right? In all those cases, your model is changing, and when this model is changing, it has implications on the way you render the system safe, right? I think this was also the message that all of us had, or the folks who presented before talked about. And you have like different ways of addressing the problem. You could have like a robust controller or a robust safety filter that have like knowledge on what could happen in the worst case. You could have adaptive approaches, data-driven learning, whatever you name it, or sensor-based approaches, right? But in this talk, we talk about adaptive control. For the ones that are not familiar with adaptive control, so you have basically two classes of adaptive control. You have direct adaptive control, where you're directly adapting the controllers, right? You have a controller with control gates, and based on what you observe in terms of like a deviation, you're adjusting these control gains directly, right? It's basically the same thing Andrea talked about in his first in his talk. So you have like classical MRAC, is mostly like direct adaptive control, and you have indirect adaptive control, where you're trying to learn or identify the mathematical model or the parameters, and based on the learned parameters, you're designing or redesign your control on the fly. So it's more or less a model-based approach to control design. There are also hybrid approaches, right? But these are like the big two groups. So for indirect adaptive control, it has certain benefits with respect to you're actually able to learn the real model and your real parameters, right? But the problem is you need sufficient excitation, right? And if you don't have it, you get problems, right? So the guarantees are weaker because you are redesigning your controller based on the model. But if the model is not sufficient enough or close enough, those guarantees are not that good. And also with that, you risk, of course, the problem of poor performance or instability, right? So you need to keep this in mind. And normally, this is an issue, right? So you can't operate in this way in most of the applications. And therefore, indirect adaptive control is not the go-to approach in the domain of aerospace, right? So what normally is done in most popular in aerospace controls is having direct adaptive control, because you don't have the strong need of excitation, right? So you can have stability guarantees without excitation and converge to local minima, which are sufficient enough. And we get the benefits, right? So in this case, we don't need to. In this case, you're having a drone that is have the problem of the induced problem of that the propellers are destroyed, right, during the operation, and you would like to ensure that the system still stays stable. And in this case, they use direct adaptive control, and you can see that without excitation, the system's able to stabilize, right? And therefore, this is like the big benefit of using direct adaptive control MRAC, right? So here again, I think you will see it. Without like adaptive control, the system is just like becoming unstable and just flies into the wall. And with adaptive control or direct adaptive control, the system stays stable, right? And actually just small adjustments and basically able to stabilize quite fast. Right, and which indicates like the performance increase, or let's say the better performance of direct adaptive control in general. Therefore, we just choose direct adaptive control as our go-to approach, okay? And now we're getting to the point where we again are in the same problem as Andrea talked about. So we're having a plant, like a linear plant in this case, and we have basically we don't need any knowledge of AP, and we know we have a lambda, which is the uncertainty on the input. But this is like also partially unknown. You know, it's like has a certain structure, but you don't know the value of it. And theoretically, you assume that there exists like this type of controller where you have a feedback gain theta x star and a feedforward gain theta r star applied as a controller to your system, right? And if when you assume this, the matching conditions come naturally, right? So this is like something we're searching for. So we don't know this, and we don't know this, and therefore we don't know this, right? So this is like our task to address, right? And the idea is like to find such controller, ensure stability, while at the same time ensure safety, right? And having all those real-time stuff being active at the same time. So I think I just like go fast through this because Andrea was already able to address this in a very nice way. So we have this reference model, right? And again, this is our controller. And now we're trying to estimate the controller gains, right? The matrices in real time. And normally we use this kind of adaptation laws to get to this point. And these are functions of our tracking error, right? The error between the reference model and the plant. Yeah.
Yeah, I just have one question. So when you're saying that these are adapting, does it mean that so it's the result of this numeric integration as at one time, or is it that you have like a family of games you are switching between the game?
These are actually basically you're integrating, right? And normally the initial value of those matrices are your nominal controller gains, right? And once you've got that, and you're having a non-zero or non-trivial error, those gains are adjusted based on that, right?
And we will have like an overshoot in the technical information.
Yeah, exactly. But normally the idea is like, so the thing is, I just switch over. So you can like using like the Lyapunov theory, right? And having some, by having this candidate in place, and with further knowledge, like using Babolat's lemma, you can actually show that this is globally asymptotically stable, right? So you actually are able to show that the system will converge, right? And you will basically converge to the right gains, right? So you will get to where are you like theta x star, theta r star, right? But you need like some things in place, right? You will can prove that the error goes to zero when you have no persistent excitation. If you have persistent excitation, you can actually prove that you get to theta x star and theta r star. But now with this, we only have like stability proof, right? But it's like this enough for us to stay safe. And I guess we all know the answer. It's not enough because like stability is not implying safety. And we got two major questions to address: where to place the safety filter and how to guarantee safety during the transient, right? And the thing is, the first question, you like from all the stuff we have known before, we would apply the safety filter where? On the control input level here, right? The problem is that when we do this, we actually destroy our safety, right? And actually also some sort of stability, but this is another problem. But the thing is, when we use direct adaptive control, all the knowledge we have on how we need to adjust due to the model mismatch or in the control input, right? Because we are adjusting the gains here, right? And then we would use a safety filter based, which is model based, but based on your nominal model, right? So actually the model knowledge here is wrong. So you're trying to correct something to mess it up again with something you have no knowledge about, right? So you can't do it in this way. So we propose like a different approach. We are using the reference model and trying to use a indirect safety critical controller. So we have the safety filter here. We're trying to render the reference model, so the reference signal safe. And with that, we're trying to make sure that the reference model stays safe. And then we're using our adaptation laws on an adaptive controller to make the plant or the closed loop system converge with the reference model. And by that, we can ensure that once the controller is learned, you're having a safe behavior, right? Because if the reference model stays safe and your closed loop system is converging with your reference model and its behavior, you're staying safe, right? But there are like some issues. If like you have a perfect plant knowledge and you don't have to adapt anything, actually you're good to go, right? So you could really say, I can render my reference model safe, and with that, my plant stays safe as well. This is actually working, but we don't have this, right? We have model uncertainties, and we have to get to the point that we have to make them converge. And with that, during the transient, we have no guarantees. What will happen is actually that that you can learn, and you could actually guarantee that the system will stay safe eventually, will stay safe again eventually, but during the transient, you could have the point that the system will escape the safe set, right? Because you don't have the right model knowledge, and you can't impose H dot on your plant at the boundary. So you need actually something more, right? And the simplest approach to do this is basically having like a safety buffer, this, right? This is the simplest approach actually. And you just need to make sure that this delta or this positive scalar constant is chosen such that it makes sure that the worst case error, the worst case mismatch between the reference model and the plants are captured, right? And if you do this, you could actually ensure safety, right? So the idea is very simple. You're just saying, okay, if I know that I'm having a certain maximum mismatch, I just need to take this mismatch, put it in between, and use it as a cushion, right? And then you're operating with a subset, and this subset is, if you choose the delta correctly, is basically ensured or guaranteed to be forward invariant, right? This like very simple approach. Yeah, so the thing is, when we so here we would have this cushion, and it will stay, right? But the problem is we're also adapting, right? So if we're adapting, we're actually able to learn the model, right? So why would we need this delta after we've adapted? So the problem is, like, from a performance perspective, imagine we're at this house in this drone, and we need an additional buffer. So the drone always needs to make like a detour, right? From a performance point of view, is not helpful. So our intent is to learn the model, but if we have learned the model, we can actually be more confident, right? And I actually should try to get rid of the safety buffer. And this is like our approach. So is there something we could do to make this delta go away once we've learned the model? Okay. And the first shot was to use this properties of gamma. You remember, like this, like the tuning parameter and the control barrier function, which actually implies or has implications of how the system is rendered safe. So we said, okay, actually we could make this gamma a function of like an error, right? The like a safety error, which is the difference between your nominal system and what you actually experience. And this function is basically just a tracking error, right? So if we're doing this, maybe there is the way to make the system safe in a more elaborated way. So the idea is like to say, okay, we have a radial basis function, and whenever the error is non-zero, the value of gamma decreases, right? And what you actually do is that you're having a dynamical estimation of your safe set, and you're adjusting the safe set dynamically based on the error you experience, right? And this is what you're doing here. We called it error-based relaxation. And Jose applied this to swarm, like I think like multi-agent cases. In this case, he had like a problem of having small agents that try to get to those spots while they are maneuvering beforehand. So their first maneuver somehow trying to get to the spots, but at the same time there are like obstacles, right? In this case, you have systems with model mismatches using only control variable function, and you see this one is hitting the obstacle. And there you have the system only with adaptive control, and you see also there one of them is hitting, which makes sense, right? There is no control variable function in place. And you see there with using adaptive control and the error-based relaxation formulation, the system can be, or those systems can be rendered safe. Yeah, this was the first shot from our side, right? However, from there, like this approach is still, even though it seems you can prove certain things, but it's still like somehow heuristic in a certain sense, right? So, and we thought, okay, we can do better. There are like better ways to address the problem. And we went further and we defined like an error-based safety buffer. So the idea is to say, okay, hey, still we have a safety buffer, but this safety buffer is only needed as long the error is non-zero, non-zero, right? If it's zero, we can get rid of it. And therefore, let's make this buffer a function of the error, right? And we can actually show that for certain formulations, if you have model knowledge, you can prove that this such a formulation is actually guaranteed to be safe. You need to have some knowledge on the dynamics, right? So you need some like Lipschitz constants on the dynamics. But if you have that and you are able to estimate the worst case error, you can show safety. There is like one caveat for the safety buffer approach, and it's like that we are able to prove that this is guaranteed to be safe on the unforced dynamics if you have uncertainties on the unforced dynamics. But if you're having uncertainties on your input, it gets more complicated, right? But we could have input uncertainties, right? So control surfaces could be damaged, actuators could not be working. So this is something we should try to address as well. And therefore, we went further and actually by having an interpolation kind of approach to the way we have uncertainties in place, we were able to address this. So the idea is like to say, okay, I know the worst case model I could have while I be on the boundary of my safe set, right? And if I know this, I could figure out the reference signal that is like needed to ensure still ensure safety, right? And this is like given here. And I also know that if I'm very far away from my safety constraints, I really don't need to take care about safety, like about uncertainties, right? The safety sense. Because like if I, let's say you have a car and your car is not the right one you expect, right? So you're normally are used to drive a Fiat Punto, and now you have a Ferrari, right? If you are very close to a wall, you would be very careful while driving the Ferrari. But if you're on the like there's nothing around you, you actually don't care anymore, right? So this is like the concept here. So if you're very much in the middle of the safe set, you don't need to care actually too much about it, and then you can just assume that you have the ideal closed loop system in place. And then you only need to figure out, is there a way to interpolate between both of them, right? And this is like what is done here. So there is like a function beta, which is helping you to interpolate between these two cases based on some model knowledge you have, right? You need to have some knowledge on the worst case error, and some knowledge on the dynamics. But if you have, when you have that, you can actually ensure that, right? And this is like done there. And in this case, then you can provide safety guarantees, right? But it's somehow also still like in work. So here in this case, Peter showed that actually it has benefits to the dynamics. So here we have like a planar point mass, spring damper. So you basically have the point mass, right? And it should tries to follow a trajectory, but there is like an obstacle in the middle of it, right? So this is like the simple case, and we compared it here with different adaptive control barrier function approaches. So the state of the art is something coming from Anuradha, their names. It's a paper from 2020 where they had like the proposal of adaptive control barrier functions, and then there was like some work coming from Brett Lopez and team, and also Jonathan Howe on robust adaptive control barrier functions, and compared the EBSB and the EBSF formulations with those state-of-the-art methods, and you can see that for a case where you have no uncertainties, actually we can have safety, but we're less conservative than the others, right? The others have safety guarantees, but they are having some sort of conservatism, and you also have some switching dynamics for the classical adaptive control barrier functions. And with applying uncertainties, the difference become more evident. So we see the adaptive control barrier function approach is actually quite conservative. The same goes for robust adaptive control, while in this actually in this case is stay safe while being the least conservative, right? This results you have seen are still really much using the classical quadratic program at the end, right? So we have still like a classical convex QP, and we're searching for inequality constraints, and with that trying to render the system safe, right? But we figured out that there's now also alternative ways of looking to the problem, right? And I think this is the last topic, and then I think we're done. So the idea is like to say, if you have a model and you know bounds, right? You know actually that your worst case mismatches on the controller gains as well as the uncertainties on the inputs are bounded, and you know the bounds, as well as you have knowledge on the dynamics such that you can get knowledge on your Lipschitz constants, right? For the error as well as the time derivative on the error. You're actually get a nice way of guaranteeing safety, right? So again, this needs, for this approach, you would need certain knowledge on your system, right? So, but if you have that, you can easily show that you can provide safety guarantees if, again, you have knowledge on L1, L2, and the bounds. But it's also a very straightforward way, because then if you know them, you can go straight forward and apply a safety filter, which is just much simpler, but it's also just a second order comp program. But now you're flipping the book and you're going from a QP to an SOCP. But the benefit is now you have a lean way of looking to the problem, right? And actually, this is the only difference. Now you have an SOCP, and with this, you can apply it into your adaptive control problem. So these are the things we have seen before, right? And yeah, with that, you can provide safety, right? And you're here seeing it for a quadcopter approach or a quadcopter system that is trying to avoid your obstacle, or it's an adaptive control system with a standard QP CBF. You're violating the constraint, which makes sense, right? And with the robust SOCP, you're actually making like a detour, so you're losing performance, but again, you're regaining it once you've learned the model. And also, yeah, it's like a nice way in looking to the problem, right? Any questions about it? No, right, it's late. Okay. Yeah, but again, these, yeah, you have a question. Okay, go.
So the proof depends on the bound of the EH.
Yeah,
And how do you actually obtain this bound?
yeah, it's through simulations. Yeah, so what we've done is, if you know you have a certain way of uncertainties, right? You could go into the simulations and apply the worst case problems, or maybe make a Monte Carlo simulation and see what is the worst case that could happen. And you're using this EH or this capital E and put this, for example, as a safety buffer, or also your knowledge on the norm. Right. So this is like the simplest approach, I would say. Yeah.
Another question is it's very interesting to see you put this sector filter on the reference.
Yeah.
The question is it imposing the safety condition on XN or actual XP? How do you transfer this?
Yeah, the thing is like, you know, like if you do it like this, can I switch over? Give me a second. So the basic ideas. So if you do it like this, right? You actually try to impose safety on XP through XM, and it works when you learn the system, right? But if you're in a transient, it's not working, right? But it's basically like trying to make an approximation of your plant models through a reference model.
So I see this is more like you're putting the conditions on XM.
Yeah.
And you want to have like XP actually follow the XM.
Exactly.
And you need to have some sort of like guarantee that XP actually follows.
So yeah, it's just like you have the guarantees once you've learned the dynamics, right? The gains. In the transient, you don't have it, but then you're trying to choose. You need to search for functions that are adding a buffer such that you still stay safe, right? So here, so the basic idea is like to say, okay, hey, I think you're seeing, this is like the basic idea. So you're saying, okay, I have my EH, which is the function of like the various values for each of them, right? And there will be a maximum value, right? Because of the stability proof on the X, you can actually figure out through Lipschitz continuity, we have a bound EH, right? And the bound would be capital E, and then you just need to make sure that HXM is always greater or equal to E, right? This is like the safety buffer you apply,
Sure.
right? And this, but it's again, right? So which is like if you learn the model, you don't need it anymore.
Sure. So you have the bound, but you also need to have like some guarantee that this bound will disappear. Right?
Yeah. So this is like the idea. Yeah. Right. Give me a second. I'll just. So, outlook conclusion. I just don't want to take too much time. So outlook is we're now at the point where we think we're able to apply the adaptive control approaches to single systems. Of what we talked about it already, like if you have multi-agent systems, the problem becomes quite nasty, right? Because now you have a chain of uncertainties that are affecting each other, right? Each uncertainty for each system will maybe lead to a wrong decision at a certain time step, which have implications on how the other systems render safe, right? And safety guarantees for that are quite difficult to obtain. And it becomes more difficult if you have like redistributed systems or decentralized systems, right? So you have no fully knowledge on, or the safety filter applied to each of the agents have not full knowledge on what the others are actually doing, right? So it's quite a nasty problem, and we try to have a look at this. And another thing is like for the stuff that is already theoretically developed, we're trying to apply it to different problems. So we're currently working to apply for hypersonic systems. There's already also work in place for this drone system. So this is something we're doing in the future. Like further down the line, the idea is like to implement everything into like a flight simulator and make an actual flights on aircraft simulators, and to in the final step make like really flight tests with like the research aircraft we have at DR, right? Yeah, with that said, yeah, so I think everything is said and done, right? So I think I don't want to take too much of your time. Something that is really like helpful. There are like really like some nice foundational work I would refer to, right? So Nagel's paper was actually the groundbreaking one, but it was actually like from the 50s and 60s, and nobody had a look on this until like recently. So it gained popularity like 50, 60 years later on. You have one of the first papers who introduced the ideas of control barrier functions. Ames did really like lay the foundation afterwards, and there are like some really good works from Weischiau, the lab of Senat, and there's also from Mark who introduced like some topics on robust in the control barrier function and foundational work on safe adaptive systems, and also the work of my collaborators and me. So have a look at this as well if you're further interested. And yeah, so again, these are Pete and Anu, right? So they like, did a lot of work in this field with me together. So have a look on their work as well. And also Jose, who showed and integrated some simulations, and Mark, who helped me with some robust control barrier function simulations. So also thank to them. And yeah, if you have any questions, like happy to answer them.